In this last video, we are going to investigate one more variation of the enclosed area problem involving polar curves. So specifically, we would like to find the area of the region that lies inside both of the given polar curves. So inside root 3 cosine theta, which is this bigger circle of the two, and inside r equals sine theta. So if we want the region enclosed between both of these curves, note that once we've solved for this value of theta where they intersect, and once again we'll do the trig or algebra to find this, it breaks down in a sense to two parts. You have this kind of blue crescent-shaped region that we could find, which would involve the area enclosed by the sine curve from theta equals 0 to pi over 3, as we'll see. And then you have this other red sliver, which would involve the area enclosed by the root 3 cosine theta curve going from pi over 3 to pi over 2. So let's go ahead and just solve for that intersection. So we need to know, where does the curve root 3 cosine theta intersect or equal sine theta? So root 3 is equal to sine over cosine, which is tangent, and this occurs specifically when theta is equal to pi over 3. So once again, for that enclosed area, this is going to involve two parts. So we first have this blue shaped region that we see. So that would be the integral from 0 to pi over 3, 1/2, and then the curve we're looking at is sine. So sine of theta squared. And that only gives us a portion of the enclosed area which we are looking for. So we also need to add on to this the area given in red. So 1/2 the integral, and we're going from pi over 3 to pi over 2. And it is the region enclosed by the curve root 3 cosine theta squared. And getting this set up, I believe, is the most difficult part of the problem, which is just breaking it up into these two different slivers where we can find the areas of them individually and then add them up. So now this becomes a highly computational problem. So let's go ahead and evaluate the resulting integral. In order to do so, we rewrite using the double angle formula for cosine. So sine squared is really 1/2 the quantity 1 minus cosine 2 theta. And we'll take care of the first integral, and then we'll come back for the second integral. So 1/2 times 1/2 is 1/4. So we've kind of pulled that 1/2 out. And then when we anti-differentiate term by term, we would have theta minus 1/2 sine of 2 theta. And we're evaluating from 0 to pi over 3. So we replace each of the thetas that we see with a pi over 3. And note, sine of 2 pi over 3 is square root 3 over 2. So this would be square root 3 over 4. And when we plug in 0, we simply get 0. So this would correspond to that first area that we had shaded on the previous slide. Now we need to move on to the second integral. So pulling the 3 out front, we would have 3/2, and we're integrating from pi over 3 to pi over 2 of cosine squared. In terms of its half angle formula, that would be 1 plus cosine of 2 theta, and we need a 1/2. Pulling the 1/2 out front, 3/2 times 1/2 is 3/4. The antiderivative would be theta plus 1/2 sine 2 theta. And hopefully at this point, the problems are starting to feel very similar to each other. You know, the difference is really in the sit-up. That's where the difficulty is involved. The evaluation is typically kind of application or applications of that double angle formula for cosine. So we go ahead and we plug in theta equals pi over 2. So pi over 2 plus 1/2 sine of 2 times pi over 2, which would be sine of pi, which is 0. Then we subtract away what we get when we plug in pi over 3. As mentioned a moment ago, sine of 2 pi over 3 is root 3 over 2 times 2, or excuse me, times 1/2 would make that root 3 over 4. And now combining everything together, we have pi over 12 plus 3 pi over 8, which is 5 pi over 24. And we have a minus root 3 over 16. And then we have, if we combine everything together, a minus 3 root 3 over 16. So 4 root 3 over 16 makes it a minus square root 3 over 4 if we cancel off the 4's in common. And this number represents the area of that desired enclosed region.